Welcome to the Getting Started tutorials of VirtualLab Fusion. In VirtualLab, we distinguish between idealized and real components. Real components have an actual description of the structure, both in terms of the geometry and the optical aspects. A very important group within the category of real components is the optical lens. VirtualLab provides different ways to handle real lenses. When the lens data is already available in, for instance, Zemax format, it can be directly imported into VirtualLab. This operation requires a Zemax glass catalog. In this session, we show a very fundamental way to construct a real lens based on the datasheet, and as an example, we take the Thorlabs Aspheric Lens 352110B, which is often used as a fiber coupling lens. It is an obsolete model with no Zemax file available from the vendor. Nevertheless, the lens data can still be found in datasheet form, and we make a summary of the necessary parameters here. It consists of two aspheric surfaces. It is made of Eco 550 at a design wavelength of 780 nanometers. In what follows, we will construct an aspheric lens according to these data. Before starting the modeling, though, it should be made clear that a full model of a real lens must include the material dispersion property. However, since this information is not explicitly provided in the datasheet, only the refractive index at the design wavelength is included, we will simply employ this constant value and use it for the design wavelength only. To build up the aspheric lens in VirtualLab, it is possible to use the optical interface sequence, OIS, which may contain any number of surfaces. Double-click on the OIS component and the corresponding edit window should pop up. The Thorlabs aspheric lens consists of two aspherical surfaces, so we drag two aspherical surfaces upwards from the bottom menu to the region above and drop them there. Then two aspherical surfaces should appear on the table, labelled with indices 1 and 2 respectively. It is not a bad idea to give the two surfaces names like S1 and S2 in the comment column. Let us define S1 first. Click on the edit icon and type in the value of the radius of curvature, 4.33 mm. Then type in the value of the conical constant, minus 0.8468796. Increase the number of polynomial orders to 6 and input the 4th and 6th order terms. 5.215123 10 to the minus 4 and 6.876629 10 to the minus 6, respectively. Finally, define the diameter of the lens, 5 mm. The Thorlabs aspheric lens is made of Eco 550. To define that, we will change the homogeneous medium behind S1. Due to the limited information available on the material, we settle by defining it by a constant refractive index, 1.597, but we should keep in mind that this is only valid at the design wavelength, 780 nanometers. Specifying the state of matter as solid for this material allows for the possible application of coatings on its surface. We then modify the distance between S1 and S2 to 5.36 mm. S2 can be defined in a similar way. Now that we have set up all the necessary parameters of the lens, it is possible to visualize the resulting aspheric lens by clicking on the View button. The two surfaces alongside the solid medium in between are automatically recognized as a closed 3D body. Based on this feature, VirtualLab will be able to perform a non-sequential tracing for a 3D optical system. Finally, you also have the possibility to save the lens by clicking on the icon on the bottom left. Following the default settings, we save it under the category My Components, and later you will be able to find this lens in Components from Catalog, User-Defined. At last, we would like to perform a ray tracing analysis of this aspheric lens. In what follows, we will quickly go through some parameters. You may find more details in the related tutorials. Use a plane wave source, set the wavelength to 780 nanometers, the design wavelength, and set its diameter to 5 mm. The distance between the plane wave source and the aspheric lens can have an arbitrary value. We use 5 mm as an example. The virtual screen is placed at a distance of 3.39 mm behind the lens, as indicated on the datasheet. For the ray tracing system analyzer, we set the ray selection method to hexapolar. Run the simulation and the 3D ray tracing result is immediately available. If you have any questions, please don't hesitate to contact us.